We'll now learn about free fall. Earlier we have learned that every body on earth is attracted by earth towards its center. The earth attracts every object on its surface or near its surface towards its center because it exerts a gravitational force on every object near it. This gravitational force is always directed towards the center of the earth. So any object close to the earth begins to fall towards the earth due to this gravitational force. So all objects falling towards the earth under the gravitational force alone are said to be in free fall. Here are some more examples of free fall, like you can see this person jumping off the cliff and the person moves towards the surface of the earth because it is pulled by the gravitational force. Here too you can see all these fruits falling towards the surface of the earth, which is also free fall. Skydiving is a very good example of free fall, where people fall towards the earth because they are pulled by the gravitational force. So again, all objects falling towards the earth under the gravitational force alone are said to be in free fall. Now, when an object falls towards the earth, there is no change in the direction of motion. However, there is a change in the magnitude of the velocity. The object begins to fall faster and faster. The speed of the object keeps increasing as it falls towards the earth. We see the speed of the body keeps increasing, and hence we can say there is an acceleration as the body moves towards the earth. And this acceleration produced in the body due to the gravitational force is called acceleration due to gravity. So if we were to define acceleration due to gravity, we would say it's the acceleration produced in a body due to the gravitational force of the earth. It's called acceleration due to gravity. There's another point we need to remember is this. Whenever there is a force acting on an object, the force is given into mass into acceleration. So whenever there is a force, there has to be an acceleration, especially when the force is unbalanced. If an unbalanced force acts on a body, that force will produce acceleration, will change the velocity of the body. And here, when the force is gravitational force, this gravitational force will also produce an acceleration in a body, and this acceleration produced by the gravitational force is called acceleration due to gravity. And the value of acceleration due to gravity, g, is equal to 9.8, and the units are just like that of the acceleration, meter per second square. Here is a good example to explain the meaning of this acceleration due to gravity. Now right out here you see a body being thrown down. Its velocity is 0. And as soon as you let it go, it begins to move towards the surface of the earth. In the first second, at the end of the first second, its velocity becomes 9.8 meter per second. Then in the second second, it becomes 19.6 meter per second. In the third second, now the velocity becomes 29.4 meter per second. But at the end of the third second, it becomes 39.2 meter per second. So what have you observed? That the velocity is increasing all the time. Every second the velocity is increasing. Now by how much is the velocity increasing? At 0 second it was 0, and then it became 9.8. That means the difference here was 9.8. Now look at the next second. It was 9.8, then it became 19.6. What is the difference in the velocity? It has increased by 9.8. Next, from 19.6, it has now become 29.4. So how much has the velocity increased? Plus 9.8. Now again, here you see at 29.4, it is further increased to 39.2. Means there is an increase of 9.8. That is why we say acceleration due to gravity is 9.8 meter per second square. As the body moves down, its velocity keeps increasing. It gets faster and faster as it moving down. To look up at the distance, in the first second, it covers a distance of 4.9 meter. Now, in the second second, it would cover a distance of 14.7 seconds. Then in the next, it would cover a distance of 24.5. Then in the following, it would cover a distance of 34.3. Observe the distance it is covering. The distance keeps increasing, 4.9, then 14.7, then 24.5, 34.3. So its speed is becoming faster and faster. It's covering a greater and greater distance at every second. So to summarize this slide, all we have to know is that whenever a body is close to the earth, it experiences a force called the gravitational force. And due to this gravitational force, there is an acceleration produced in the body. And this acceleration produced in the body due to the gravitational force is called acceleration due to gravity. We'll now find the relation between the small g, which is acceleration due to gravity, and the capital G, which is gravitational constant. For this, let us consider an object, say of mass m kg, kept at a distance d meter from the center of the earth. So the small m denotes the mass of the body. The capital M will denote mass of the earth. The d, the distance of the body from the center of the earth. So let us mark this. So we have this is small m. We will mark this as a capital M here, the mass of the earth, and the distance, this distance till the center of the earth, we mark as small d. By the universal law of gravitation, we know there is a force acting between these two objects, and the force is given as F equal to G, mass of the earth, mass of the object over the square of the distance between the two objects. Now this force is also given by Newton's second law, and Newton's second law says that the force F acting between these two objects is mass into the acceleration due to gravity. Now both these forces are one and the same, so we equate the forces. So we say F equal to F, the force mg, this is by Newton's second law, which is also equal to gmm over d square, given by universal law of gravitation. And if you notice here, we can now cancel off the m on both the sides. So we have g equal to gm over d square. The g is acceleration due to gravity. This capital G is gravitational constant. M is the mass of the earth, and d is the distance between the object and the center of the earth. So the expression g, which is acceleration due to gravity, is given as g m over d square. However, if the object is on the surface of the earth, m is the mass of the object, capital M is the mass of the earth, and now the distance will be the radius of the earth. This distance here will be r, and in this case the g will be g m over r square, where r is the radius of the earth. Now we'll go ahead and see how to write this derivation. Now consider an object of mass m, we'll write m, kg at a distance d meter from the center of the earth. The body experiences a force of gravitation F, and hence it is accelerated towards the earth with an acceleration g. By Newton's second law, we know that force equal to mass into acceleration. So in this case, a gravitational force F equal to m into g, because g is the acceleration due to gravity. This is equation 1. Now if m is the mass of the earth and g is a gravitational constant, then by the universal law of gravitation, the force between the object and the earth is also given as F equal to g m over d square, where d is the distance that we have already written earlier, distance between object and center of the earth. This is equation 2. So from 1 and 2, we can say that F is also equal to this F. It's one and the same F. So we can say that mg is equal to g m over d square. We cancel the m on either sides, and we now get that g equal to g m over d square. This is the expression for acceleration due to gravity. So here basically you find out the force in two different ways. Like here you find out the force with Newton's second law, and you find out the force with universal law of gravitation, and then you equate both the expressions. So we have seen that the gravitational acceleration due to gravity is given by g m over d square, and if we are close on the surface of the earth, then g will be equal to g m over r square, where r is the radius of the earth. This is on the surface of the earth. It's important to note that the mass of the object is not in the expression at all, which goes to say that acceleration due to gravity does not depend on the mass of the object. So this is an important point. Acceleration due to gravity does not depend on the mass of the object, which means now we have two objects, say one of 10 kg and another object of 1 kg, both falling towards the earth. What would you expect? You'll probably say the heavier object will move faster and reach the earth quicker. But you are surprised, no. Both the objects will reach the earth or the surface in same time. They will take same time to reach the surface of the earth, and the reason is because g does not depend on the mass of the earth or the mass of the object. It depends on the mass of the earth but does not depend on the mass of the object. So from a helicopter, if you were to throw a large object of say 100 kgs and a small object say of 1 kg. Both will reach the earth at the same time. Here we see Galileo at the top of the Leaning Tower of Pisa, and he is dropping two objects, a large object and a small object from the same height. And to his surprise, he found both the objects traveled together and reached the surface of the earth in same time. He expected the larger object to reach first and then the smaller object to go slower. But no, both of them reached the earth in the same time, because acceleration due to gravity does not depend on the mass of the object. So in the last slide, we learned that whatever may be the mass of the object, both will fall to the earth in the same time. Now if you try this experiment, you take a coin and you take a feather. You go to a certain height, maybe on your terrace, and drop the coin and the feather. What do you expect? Do you expect both of them to fall to the earth at the same time? Is it that what you will observe? No. You will find that the coin falls straight down while the feather does not fall straight down. It just flies away like this slowly and then comes to the earth. So what happened to the concept that objects fall to the earth in the time regardless of their mass? Here we expect the coin and the feather to fall to the surface of the earth in same time, but that did not happen. Why? Now, however, if this coin and the feather were dropped in vacuum, it was found that both dropped down in the same time. So who was making this difference in the behavior of the coin and the feather? It was the air. Now the feather has a large surface area. Its mass is spread on a larger area and hence experiences greater air resistance. The coin has less surface area and experiences less air resistance. Hence the feather takes longer to reach the surface of the earth compared to the coin. But when it comes to the vacuum, coin and the feather both reach the earth, the surface, at the same time, because there is no air resistance here. It is vacuum. The concept of air resistance can be very well explained in skydiving. If you notice, the skydivers, before they reach the earth, they pull out their parachute, and because of this parachute, the air resistance increases. There is a resistance offered by air in the upward direction, and hence the person then falls very slowly to the earth. In this picture, you see how the skydiver spreads his hands out and his legs out, and this is because to increase the air resistance, and because the air resistance increases, he then slowly falls towards the earth. Again, in this picture, we can see the air resistance acting upwards, the gravitational force acting downwards, and that's why he spreads his hands to spread the surface and increase the air resistance. When he uses a parachute to the next picture, the air resistance further increases and the gravitational pull becomes less. So he very carefully, very gently falls to the surface of the earth. When we go back to the feather, the same thing happens to the feather. The air resistance experienced by the feather is more because it is spread out, while in the coin the air resistance is less. It would be interesting to note that the acceleration due to gravity on the earth is not constant. At the polar region, the acceleration due to gravity is different than the equatorial region. Now let's see the reason for this. And the main reason for this is the earth is not a perfect sphere. As you can see in the picture, it is bulging at the equator and flattened at the poles. See, it is flattened at the poles and bulging at the equator. Hence, if this is the center of the Earth, this would be the polar radius. And this polar radius is much less than the equatorial radius. So we write it as small r for the polar radius. The equatorial radius is here and is much longer. So here the equatorial radius we'll put it as capital R. And you can see here from the figure the polar radius, this is the value of the polar radius, and for the equatorial radius here is a value of the equatorial radius, and it is obvious from there that the polar radius is less than the equatorial radius. So at the pole, the g at the pole would be gm over r square, a small r, because the polar radius is less. But at the equator, the acceleration due to gravity at the equator will be gm over r square. So acceleration due to gravity at the poles is gm over r square, where r is minimum, and at the equator is gm over r square, where r is maximum. So at the pole, the g will be much greater than the g at the equator. Let's go over this point again. So we said the polar radius was small. So at the pole, the g was gm, and I will use a small r. But at here it was much longer at the equator. So the g at the equator, we call it E, is gm over r square. If we compare this both these values, which value will be greater? Let us compare them. So I have gm over r square at the pole, and at the equator I have gm over r square at the equator. Look at the denominators. Here this denominator is small. If the denominator is small, the fraction becomes larger. Here the denominator is large, so the fraction becomes small. So who is smaller? We will have to put it this way. The g at the pole will be greater than the g at the equator, and the reason is the polar radius is less than the equatorial radius. And why is it so? The Earth is not a perfect sphere. It is not perfectly, all the radius are not equal. It's not a perfect sphere. It's bulging at the equator, hence the equatorial radius is more, and flattened at the poles. So the polar radius is less. So if this was the Earth, it's not a perfect sphere like this. It is flattened at the poles and bulging at the equator. So the Earth is something, isn't a very exaggerated figure. It's not exactly like this, but just to exaggerate, this is how the Earth is. Here is much less. This radius is small. this radius is large. Therefore, the g here at the pole is greater than the g at the equator. In this case, since the radius, we said the denominator was small, here the fraction will be large. Here the denominator was small. Here the denominator was large, so the fraction is small, and hence you got this greater than sign.